Okay, so I guess we'll hop right into the first data type. So we have STD arrays. So STL arrays are basically, they're just objects wrapping around regular C-style arrays that we just learned about. And they just implement some handy methods and operators to make your life a bit easier. And you can even pass them by value. So like you can return arrays from functions. Um, and like it's not like just returning the pointer, like it actually returns all the data. But it's kind of sus. Like it's considered bad practice to return arrays. Returning the pointer is like, people prefer it a lot more. So probably not a good idea to do it, but you can if you want to. So yeah, we'll just hop into some example code here. You guys can all see that, right? Yep. Okay. So at the top we have the includes, but yeah, you can just do the bits stdcpp thingy that Trevor just talked about. That will work too. So first thing we do in main, we define an std array with these numbers in the array. So let's break apart this statement and figure out how this works. So we have an std array data type, but then we also have to specify what actually goes inside the array. So that's what these angled brackets are. They're called template arguments, and they basically specify like the specifics about the array. So in this case, it says that the array has the integer data type and it's of length 7. So yeah, when you define an array, if you want it to be a different data type, you have to put something else here other than integer. And if you want a different length, you just put that length in here. So it requires 2 template arguments. One is the data type and one is the length. And then the name of the variable, which is just ARR. And then we can set it equal to our data with the curly brackets, and then that will work. And then some methods that it includes, you can do dot size. So before, remember, you basically had to know what the size was, or like in some cases you can use size of, but not always. Well, when you use std arrays, you can always do just dot size, and it will just give you the size of the array. So in this case, that's 7. We have 7 elements here, right? And then if you want to get the first element, it's the same thing. You just do the square bracket 0 and print it using cout, and then follow that with a new line as always, and then that'll print this on a new line. And then you can also use range-based loops. So these might look a little funky if you've never seen them before. Basically, it's the exact same. You know, you might know your like you do like for int I equals 0, I smaller than the size I plus plus. It's literally the exact same thing, except basically C++ automatically assigns the value. So this loop, basically, it iterates over each of these values as x, and then you can do stuff with x in there without having to worry about like an index or whatever. So in this case, we just print it, and we add a character, and then at the very end, we add a new line so that they're all on the same line. And they can also be assigned to each other. So you can do some variable equals the array. Keep in mind that this cannot be done with regular C-style arrays. So if you like, remember that C-style arrays are just pointers to the first item in a block of memory. It's important. If you did ARR1 equals ARR2 with C-style arrays, you're basically you're not assigning ARR1 with the same data. You're just assigning the address to it. So it doesn't copy the contents into a new memory. It doesn't do any of that. It literally just like pastes the pointer that is AR2 into AR1. And with std array, it actually makes like a separate copy of the data that you can do other stuff with. So that's what this is here. And then remember I said that you can use like auto and stuff too. So you can also do auto ARR2 equals ARR because your compiler already knows what the data type of ARR is. So it can guess what the data type is, and that's where auto is used. And so arrays also implement iterators. Yep, I talked about that earlier. You can use range-based loops. So you can do std algorithm functions with them, like sort. You can sort arrays. So that's why we included algorithm up here. So then you can call sort on the begin and then on the end of the array, and then it will sort all the values in between. And if you don't know what iterators are, don't worry. Trevor will cover them shortly. But yeah, they're like fancy indexes basically. And then you can also access the first and last elements using functions, just dot front and dot back. Super simple. You don't have to do like square brackets, dot size -1 or something like that. And then you can fill the arrays with any value you want. So I can fill all the values with 2. That's what I did here. And if we run that, give it a second. So yeah, you get the size 7. we get the first element, 5, which lines up. We print all the elements, which is the same thing we typed in, so that works fine. And then the front and the back of the sorted array, which is 2 and 10. Those are the smallest and largest values. So yeah, that's pretty much arrays in a nutshell. They're the exact same as C-style arrays, but they implement some nice functionality to make your life easier. Yep. Any questions with them? The ones he censored, I'll be talking about them anyway. They're just the lists and the forward lists, but they're kind of useless anyway. But I'll cover them quickly. So anyway, after that, we have std set. So it's another container, just like the array. And the big point is that all elements inside the std set must be unique. So you can't have duplicate elements inside a set. And that's because sets are associative, which means that you get elements with a key instead of an index. More specifically, the keys are the elements themselves. And the elements are always ordered, so sets automatically sort elements whenever you add them to the set, which might sound inefficient, but they maintain their elements in something called a binary search tree, meaning that the insertion is logarithmic time, which is pretty good for L notation. So here are a couple useful methods. You can always consult the documentation. Yep. So we have .insert, inserts an element into the set. We have .erase, which erases an element from the set, and you can get .size, which returns the number of elements in the set. And I haven't looked over Trevor's code, but we might as well give it a quick review. So we have our includes, but then yeah, you can also do this special thingy, which he talked about, and you can include it to avoid typing up all that crap up here. So then we have our main. We define a set of floats, float data type, called foo. And in foo we insert 2.9, 1, 60, 60, 5, whatever, some values, and then we can use foo.size to get the size of the array, which in this, of the set, which in this case is just 5. And we can use iterators to loop through sets. So you can use, this whole thing here. You can just type in auto instead of this, but yeah, technically the type is a std set float iterator. You have to type in this whole thing or auto. Auto will also work in this case. So for, you loop over that, you increment the iterator, you can dereference the iterator to get the value, and then it will print that. And then do not update the value at the iterator. Big bad corrupts the data structure used to maintain the order of the set. So yeah. Basically, yeah, that means that you shouldn't assign things using the actual iterator. Like, don't do .iterator equals, or sorry, star iterator equals something, like to actually assign to it, or else you'll mess things up. Apparently, I don't use sets very often. So anyway, std set float iterator equals foo.find. So this returns an iterator to wherever 2.9 is stored inside the set, and if it isn't found within your set, this is important. It returns the iterator to the end, to the last. It's foo.end. If it's not found, so you can use that to check. Basically, like, you can do this .find, then you can do if the iterator equals foo.end, then you know it's not within the set. And then you can also do foo.erase 2.9 if 2.9 is the set. And you can also erase iterators as well if you have an iterator to some value you want to erase. And there's also unordered sets. I think he had a slide for that actually. Oop. Maybe not. So it's the same as a normal set, but it doesn't keep order. So we'll send help. Send already exists, so it does nothing. And then you get this .size as well. Yeah, you can do the exact same thing as in sets. You can do .find, but it's not ordered. So yeah, if you iterate through an unordered set, things won't be in order. Yep. So okay, yeah, so he didn't do all this, but it's the exact same functionality as a set. A lot of these STO containers have the same methods. So once you get used to like the insert, .size, etc., you basically know how to use like a decent chunk of all of them. And then there's also maps, which is the next thing. So I'll go over that. So maps are exactly the same as sets, except they use key value pairs. So it's like a dictionary if you know Python. So you can use the key to get the value instead of using the value to get the value. And the key must be unique, but you can have multiple same values. Like you can have different keys with the same value, but you just can't have like multiple keys with like different values. Like there's no way for the computer to tell which one to give you, right? So you have to have unique keys. So oh, this is the same thing, right? Yeah, okay. So yeah, you have a map that takes strings and maps it to floats. So this is like a Python dictionary you can think of, where the keys are strings and then your values are floats, and then you can insert a pair of a key and a value. So you need to use make pair. Actually, I'm pretty sure you can use curly braces here, but yeah, it looks better if you use make pair. Like it's more better form, I guess. So yeah, you can use make pair to insert key value pairs into it, and then you can do like foobar, square brackets, key, or like it might be a dot get, and then you can get the value pair. You have to consult the documentation, but yeah, it's basically just a Python dictionary, but in C++ and with some different things. So I see Eric's out had a question. If you do foo.find, very last element of the set, would that return foo.end or no? It won't. It'll return the iterator just before it. Foo.end is like the last element plus one. It's like it's technically outside of the actual container, which is weird, but that's for some reason that's how it was coded. Yeah, so foo.end is like outside of the actual container. It's like the end plus one. So yep, let's keep going from here. And there's unordered set, the exact same as a set, but the order isn't kept. It's implemented using a hash map instead of the binary search tree I mentioned earlier. So hash tables don't keep order, so unordered sets don't keep order. But on the bright side, hash tables have O1 insertion and access times, so like it's constant time for keys, which is pretty nice. And then yeah, I talked about those earlier. So there's also unordered maps as well, and those have their own pros and cons. And then there's multi-set as well. It's a set, but you can have multiple of the same element, and that's the only difference. So next up is the stack. Well, not the stack, like the stack data type. So STL stacks are objects which implement the stack data type. So this is a LIFO data type, if you heard of that. It's last in, first out. So you can think of it like, if you haven't heard of the stack data type before, it's kind of like a pile of books. You know, when you add books, you stack them on top of each other. And then when you take them off the pile, you take the one at the very top off first. And then you keep going from the top down, basically. So the last one that goes into the pile is the first one you take out of the pile. And so they're pretty simple. They're a common data type, so you may actually end up using these, unlike some of the other containers we'll talk about. And yeah, it's nice that they've created it so you don't have to create your own implementations. They're dynamically sized, just like vectors, and the other ones except arrays. You don't have to specify size when you create a stack. And we'll just check out some of my code here. So yeah, common theme, you have your include statements at the top. Then there's this new function I wrote to print a coordinate pair, which is literally just a pair of integers. I use that because the stack I have, for this example, I used pairs, but this can be anything. You can use any data type in there, right? So this function here, print coordinate pair, it takes a pair of integers named coord, and it prints them in this, like in the way you would see like Cartesian coordinates, like, you know, curly bracket, first number, comma, space, the second number, that. So you can see how it does that there. It's pretty simple. You use dot first to get the first element in a pair, and dot second to get the second, and then yeah, pretty straightforward. So we use that through to print some of the stuff. So anyway, onto the actual code, the main code. So we define a stack of pairs of integers. So we just do std : stack, and then in the template argument we put our data type, and our data type is a pair of integers. So you can see how there's like nested template arguments in here, which happens whenever your data type also needs templates, right? So in this case, you know, we want pairs, but you also need to say what the type of the pairs are of each element is. So, and then we call it stack with 2 C's. And then we can push objects to the stack. So yeah, you can see how Trevor used make pair before. It turns out you can also just use curly brackets, and then C++, like the compiler will automatically know that you mean to make a pair here, and then it'll do it for you. So in this case, if I'm pushing a pair to the stack, I don't have to write all that std ::make pair thingy, I can just do curly brackets and push it to the stack. So we push the 2, 3 pair 1, 2 to the stack. And then we can also do something called emplace objects in the stack. So if you use this intelligently, you can get some big performance gains. Basically, if you're adding an object to the stack, but you don't need to use it except for when you pop it, like at some time later. You don't have to use it in between or like before or whatever. You don't need to push it to the stack. You can just straight up like create it in the stack, basically. That's what emplace does. So instead of passing in your object, you pass in the parameters that C++ will need to create your object. So in this case, in order to make a pair, you just need to know the first and the second value. So we give the emplace function the first value and the second value, and it will create the object into the stack directly, and it's much faster, usually. And then, yeah, just like the other STL containers, we can get the size, and we can print that. We can print the element at the top of the stack using the print coordinate pair function we defined earlier. We can pop elements from the stack, which just deletes the top one. And then we can print the new one, which will be something else. And then you can assign them just like std arrays. You can just assign them to, and it will copy the data. And then you can see that here. So if we just print this, you can see, so the first time we printed value on top, then we popped it and we printed the next one. So you can see it should go 4 to 5, then to 1 to 2. That's exactly what happened. And then at the bottom, we printed the top again. There's them. So I guess, actually, any questions before I move on? Oh, I see Eric asked one. Is there any benefit of using built-in stacks, queues, and C++ over simply making your own vectors and using .pop and .pushback? So often the containers are optimized for that. So yeah, it's likely that the stack implementation, like the people who made that thought about it and somehow made it faster. The people who wrote this are obviously pretty smart. So yeah, there's often like little optimizations that make them like slightly faster, but all in all, it's just like simplicity, and it doesn't. You can use vectors. There's no reason not to, other than I guess it just sounds cool using stacks. I don't know. No problem. No problem. Good question. So let's move on. Then there's std queues and dequeues. I'm gonna try and pick up the pace here. I don't want to take up too much time. So STL queues are objects with the FIFO data structure as opposed to LIFO. And they're virtually identical to stacks, except that stacks are LIFO, remember that? So it's last in, first out. You take from the top of the pile first, whereas queues are FIFO. So you take from the first, like the bottom of the pile first. So it's kind of like a line of people. It's always the first person in line that goes first, right? You don't have people from the end of the line going out first. But in a stack, that's what happens, right? It's like a pile, so you take it from the top first. So that's the difference. It's basically just like you take it from different ends of the pile. And there's also dequeues, which they're double-ended. So basically, you can push and pop from either ends. And they're a bit slower doing that than the stacks and queues. So if you only need to pop from one end, you should probably use one of the two. But if you do need both ends, you can get dequeues. And the code can be found here, but you guys can look that over after. I have comments and stuff, so you can feel free to ask me questions, but I think we're running a little bit late, so I don't want to keep you guys here too long. There's also priority queues, which are similar to STL queues and stacks, except that their data structure is neither FIFO nor LIFO. It's actually ordered by the largest element, so if you call .top, it will return the largest element in your priority queue. So, and by default, it's ordered by the largest element, but you can also change that. You can use your own custom comparators. You can see that in the documentation. It's a little funky. And they offer constant time lookups, so .top runs in constant time. It's really fast, but you pay the price when you push to a queue, which it's not that bad. It runs in logarithmic time, but something to consider. Actually, yeah, before I move to lists again, anything? Nope. Right. We'll move back here. Okay, so lists and forward lists are our last thing. So STL lists, they're containers with linked list data structures. So basically, in a linked list, each element in your array has like basically has a pointer to the next element in the list and the element before it. So it's kind of like a chain. Each element tells you where to go next, or if you want to go backwards. And that's in a doubly linked list. There's also singly linked lists where it only tells you how to go forwards. That's what STL forward lists are. So in STL forward lists, you can iterate forwards, but you can't go backwards because the pointer for the element before isn't stored with the element. So yeah, so STL lists you can do bidirectional because they know where both sides are, right, at each element, each direction. But STL forwards it only tells you the forward direction, so you can't go backwards. But they're more space efficient in that sense because, yeah, you don't have to store that backwards pointer. So there's some example code as well, and there's documentation. Again, we'll paste the links in the chat, but yeah, you guys can read it, ask me questions, but we're running pretty late, so I don't want to keep you guys longer. STL lists are kind of scams. Like I don't really use them. Like vectors, yeah, like Trevor said, they're basically what everyone uses, and I guess arrays sometimes. Lists are kind of scams. If you think they're like Python lists, like it's not true. Python lists, like they're nice. STL lists, like you can't use square brackets on an STL list. You have to like iterate through the whole thing, and there's some convenience functions, but all in all, it's just not. It's only really good if you have to insert a lot of things into your data structure. If you don't have to do a lot of insertions, it's not really efficient. Yeah. So, and if there's any overall questions or questions about lists or anything, feel free to ask me. Okay. You can also PM Trevor or I or some of the other execs about any questions you may have. So, next. So yeah, that was a giant info dump. We're gonna post the slideshow into the classroom for you guys to use as a reference. Yeah, you're not expected to like remember all this. Like, there's no way. There's a lot of info, but as long as you remember some of the general details about how data structures work, over time, if you practice, you can figure out how these work. But all in all, just make sure you know how to use vector basically and like C-style arrays, and you're pretty set. Good way to learn. You can practice doing like CCC problems or like HackerRank or whatever, or LeetCode, and yeah, you can if you practice doing them in C++ as opposed to like a language you're more familiar with like Python, you'll figure out how to use them. I guess you gotta learn by doing basically. So yeah, thank you so much, guys. We'll be uploading this video to YouTube shortly, and yep, that's it. Meeting's over.